Okay, and then actually, let me find. Do I have the book? Did I ever open the book in this computer? What's our book called? Gerstein. There it is. Okay, I'll just show you. Yeah, I think section. It's like section. Yeah, 2.6. Hold on. Let me share screen also. Okay. Yeah, so index sets. Okay, so I'll do some examples. I just want to show you, like, there's something I'm going to show you a little bit later. Yeah, that, like, the idea is that we can, if we have a bunch of sets, we can sort of list them by a subscript instead of just having, like, I think this was sort of an example of, like, you wouldn't necessarily want to have a bunch of sets with different letter names. It's better to just give like a subscript. And I'll give some examples in a moment. But and I'll show you something else on screen in a moment that I don't want to write. I don't really want to go through writing on the board. But yeah, so let's go to the board. All right. So, okay, let's talk about index sets. So let me just give an example. It's a collection. Well, let me just say in general, this an index set of index sets is a collection of sets labeled with subscripts where the subscripts themselves come from some indexing set. Come from an indexing set I. So I'll give you a bunch of examples. So one class examples I want to talk about is something like, what if I just wanted to consider the set of all vertical lines in the plane? The set of all vertical lines in the plane. Well, we could define, I mean, so like there's lines of the form x equals constant, right? So I could define like L sub 3 to be the line x equals 3, or L sub negative 100 as the line x equals negative 100, right? So if we want to list them all, you'd want to give some sort of index. So like L sub 3 equals a set of, I guess, x and y in R2 such that x equals 3. L sub negative 100 is the set of x and y in the plane such that x equals negative 100, etc. And so we can think of this, the set of all vertical lines, as the set, maybe I'll call it, so this set of all vertical lines we could think of this as the set of L sub, I don't want to use x because it's kind of, x is kind of being used here, but let's just say L sub A, where A is in the, sorry. And so the usually what we do is we write something like this. We sort of say this right here is the indexing set because, right, we can pick any real number on the x-axis to be our point that it passes through. So this is the indexing set. But notice what we do is we sort of list the indexing set there outside of the curly braces. Just again, it's a notational convention. But we just make sure, I mean, I think that's what the book's doing, but yeah, you can see it like right here, right? Like this is the kind of generic way people write things down. So we write, I guess we write the set of all vertical lines as this, where you might need to specify what we mean by L sub A, and where L sub A equals the set of X and Y in the plane such that X equals A. Right, so it's a set of sets, but we listed by an indexing set. Okay. Another example, just another maybe like a little bit even more concrete example. Oh yeah, sorry. If there were no parentheses here? Yeah, would like X and Y be like... Oh, I guess they would both represent elements of R2, so they would both be two-dimensional points. I guess so. I guess that's true. Yeah. I would feel like that would be sort of bad notation just because like we're so used to using X and Y as the X and Y coordinates, right? But no, you're right. If we wanted to specify 2 points in space, we in the plane, we could. I guess a lot of times I write vectors, like, you know, maybe I would say like X1 and X2 and R2, something like that. Or you could just say P and Q if you just recognize that these are points, you know, but then P itself would be have an X and Y coordinate and Q itself would have an X and Y coordinate. Right. No, but it's a good point. Like the parentheses are important there. Otherwise, I'm talking about 2 separate elements of R2 rather than 1. Yeah. Okay, so like I said, a little more concrete example I was thinking about was like, what if we had S1 is the numbers 1 through 10. S2 is the numbers 2 through 11. S3 is the numbers 3 through 12, and so on, up through say S8. I don't know, just pick the random place to stop. I guess I should have dot right here. 8, 9, 10, up through 17. Is that the pattern I'm writing down? Right, I mean, this is kind of a random thing to do, but I'm just saying we can make these 8 sets of 10 consecutive numbers, right? And so we could write this collection as, you know, the set of SI, where I is in I, little I is in big I, and where big I is what? What's the indexing set here? So I'm just stopping at this one. What's my indexing set? Yeah. Yeah, I'm not meaning this to be a trick question. And just like, it's just 1 through 8, right? I mean, you could try to let this keep going forever and use the integers as your indexing set or something, or the natural numbers. But here I'm just saying like, I'll even write it all out. It's that set, right? And you could, I guess you could say where SI is, I guess if you wanted to give a definition of it, you could say it's the n in the natural numbers or in the integers such that I is less than or equal to n is less than or equal to, or maybe less than, wait, am I doing I plus 10 or I plus 9? I guess if I want 10 things, then that's what I'm doing to get. Yeah, because this is I plus 0 through I plus 9 is actually 10 numbers, right? Does that make sense? It's kind of contrived, but one reason I wanted to put this here is that we also will often talk about intersections and unions of a set of index sets. So And here's a good example. So I'll give you a formal definition, or like an abstract definition first. So given some abstract, set of index sets, set of A sub I, where I is in little i's and big I, we can define the union. And what we do here, it's kind of like summation notation where you use that big sigma for the pluses. There's like a big union symbol, like we can use, so we're define the union, and we use this kind of symbol. And that's defined to equal the, again, like all the AIs are in some universal set, right? Just to give us a place to put, not in a subset of a universal set. So this is the set of all X in the universal set such that X is in AI for some I in I, some little I and big I, right? I could say there exists, I could also say there exists a little I and big I such that X is in A sub I. Because it's an or, right? As long as it's in one of them, we want it to be in the union. Try that. So or we could say there exists an I in I such that X is in A sub I. That's equivalent, right? And then the intersection, we could define the intersection, and we the big intersect sign. You start to see this kind of thing more and more. Anytime you want to do more than one of something, you just make the symbol bigger and stick it in front. I guess summation should just be a giant plus instead of a sigma. So this is, can you guys tell me what this is going to be? The X and U such that the intersection. Yeah, it's just for all now, right? Because it's intersection. So you could say X is in AI for all I in I. Okay, so that's the intersection. Set of index sets. Make sense? Any questions? So if we go back to this example, we could look at the union and intersection, right? So back to the example above. What is the union I and I of S sub I? By the way, we could write that kind of like summation notation, I equals 1 to 8. Like you would with summation notation, where the bottom thing is where you start and the top thing is where you end. You'll see stuff like that written too. But what is it in this case? What's the union of all these sets? Yeah, just 1 to 17, right? And the intersection, you could write that as I equals 1 to 8 since it's a finite set here, or just a listable set, a countable set. What's in the intersection? I've heard from you like 5 minutes ago. I'm sure you know. I'm just something in front of people. What's the intersection of all these sets? Someone tell me. What's in all of them? Yeah. 8 is in all of them. What's that? 8, 9, 10. Is that in all of those sets? Yeah. Is there anything else in all of them? Good. So it's just 8, 9, and 10 is in all of them. Good. Okay. So that's the idea. You can get some interesting, fun things like for example, let me just do one more example. It's actually an interesting. What if, yeah, let's do one more example. That's sort of a famous infinite example. Questions if you have them. So this is actually something that comes up in analysis, which is Math 2603, real analysis. So example, suppose, well, right, let me just do notation, right? So A to B, this is a different A comma B. It's actually really annoying. If you do closed intervals versus open intervals have the same notation as like a point in space, right? So if this is the notation for the open interval, which is the set of X in the real numbers, such that X is strictly between A and B, and this is the closed interval that allows the endpoints to equal, right? By the way, I think in other countries they actually use this notation. Like they kind of reverse the brackets for open. Anybody seen that? Just because this is this. You need the context to know whether you're talking about an interval or a point in the plane, right? So let's let, well, you could think about the set of open intervals -x to x, where x, I mean, I could even write it this way. I want to do this, but where x is between wait, how do I want to say this? I was going to say x between -1 and 1, but then that's kind of, I don't want that to be negative. Let's just say 0. Right, so you can do things like this. I could actually just write this as like the interval. I could just write, like specify, this is sort of my indexing set, is this set of things satisfying that. Actually, sorry, I want that to be, yeah, I can't do a closed interval from, that's an empty set. If I put 0 here, the interval from -0 to, open interval from -0 to 0 would be empty. There's no number that satisfies strictly greater than 0 and strictly less than 0. Right, so this is an interesting, so you're basically taking all these intervals around the origin, around 0. Yeah. And so my question is, what is the union and what is the intersection? The union and the intersection. Think about it for a minute, maybe talk to people around you. See if you can convince yourselves. I guess all I'm doing here is saying like, sometimes people put open bubbles to mean like not including the endpoint. Now you can do like infinite unions and infinite intersections. Do people have answers? What's the union? Yeah.
Would it be the set -1?
The open interval or the closed? The open interval. Yeah. I think these are all growing, right? These are all inside the ones bigger than them. So this is just -1 to 1, that interval. I'm sorry. Oh, wait, actually, yeah. Oh, that's interesting, actually. There's actually something interesting because this is not one of the sets. Yeah, there's actually something still interesting there, right? Like -1 to 1 is not one of the sets in this. But do you believe that this is still the answer? Yeah, why? What's the biggest I can make? I mean, is there a biggest value I can make X? No, you just keep making it 0.99999 more, and so that it's going to eventually swallow up everything between -1 and 1, but not get to -1 and 1, right? What about this? Oh, sorry. Go ahead. Oh, but this interval contains 0. Right. This is like if we did negative, like this interval is the interval from -1 to 1, so it contains everything between -1 and 1, including 0.
But if an X cannot be 0.
But so you're saying like 0 shouldn't be in here or something?
Because like our X is from 0 to 1, and 0 is not included.
That's right. So we don't include that interval, but if you just think about the fact that every one of these intervals, everything in here includes 0, right? All of these intervals contain 0 as a specific point. So, and we're just taking more, we're just like taking the union to get more and more of them. So 0 is in every single one of these. Does that make sense? Or what am I, does someone else think see what I'm missing? Like if this was like -1/2 to 1/2, right?
When we declare like X at 0 less than X, so the smallest X can go is like 0.00.
That's right. But so okay, so if you had that like -0.00001 to +0.00001. That's a tiny little interval around 0. So it contains 0 inside it. Am I doing something with the notation that's weird? Right, this is all the numbers between these two numbers?
I understand that.
So when we're, okay, yeah, you're just looking at it weird. It's easy to do. Yeah, when we're unioning all of these, we're just kind of taking them all together, right? Like, so we're just taking anything that's in any of them. Okay, good. Now what about the intersection? What were you gonna say? Oh, Adi. Just 0? Yeah, so is that the only thing that's in all of these? So we were just saying, right? Like it's the only thing that's in every single one of these is just 1 point, right? Because like we can make these as small as we want, like you're saying. And so we can everything non-zero is eventually outside of one of these. Because we can just shrink it down further and further and further. Yeah. If this was closed, oh, that's interesting. Well, okay, I still think you can make the same argument that like, so you're saying like, if we looked at the alternate version of like negative x to x like that. There is no such point, right? So like you basically, you could, I mean, you can sort of prove that like this is still just 0 because like if y is not equal to 0, can you tell me an interval that around 0 that y does not live in? Like if I put y here, can you give me an example of an interval? That this does not live in around 0? Going with this. Yeah. Yeah, y, yeah, negative 1/2 y to 1/2 y, right? Y is not in negative y over 2 to y over 2. For you to say something similar? There's no such, yeah. And this doesn't matter. This would be the same if it was closed, right? So in fact, yeah, these kind of give the same intersection. But I guess what's interesting here, that these are infinite unions and infinite intersections. And it turns out that an infinite union of open intervals is always open, called open. Like what makes it open? It's kind of, I don't know, I'm almost giving you like a preview of math, of real analysis, but is that a question or you just? Okay.
For the yellow one at the bottom there,
Uh-huh.
under the intersection, would it be 0 less than equal to x?
Oh, I didn't change that. I mean, we could look at that case too. I don't think it would change. You're right that now we could include 0 because this would not be empty anymore. I don't think it has to be equal 0 because it's still going to be the same thing that like any y that's not 0, it's not going to live in that interval. So therefore the intersection is just the number 0. But we call sets open if there's if you can wiggle a little left and right and still be in the set. And they're closed if not, if there's like boundary points. And so this is an open set. This is a closed set. And so it's interesting that an infinite union of opens can be open, but an infinite intersection of opens can be closed. Not important for this class. I'm just sort of trying to give you like stuff you're going to see in the future if you go on and take real analysis or topology or these kind of things. It's kind of an interesting, this is something that comes up. Like, are you allowed to take infinite unions or are you allowed to take infinite intersections? And it's like, it can become hairy. It becomes hairy when you start trying to do infinite unions and intersections. And you can this is maybe the first example where you see something kind of wonky happens, or you don't get an open interval anymore. Anyways, okay, cool. Makes sense. Yeah, this is kind of fun to think about. I mean, a lot of real analysis is like this, it's called the point set topology of the real number line. So. And you could actually define stuff about limits often in terms of these like intervals and stuff. If you want to get into like rigor, because what you do in real analysis is you prove a lot of the stuff in calculus rigorously. And so this stuff gets, this is almost like a limit of some sort of intersection of things, you know. So, okay, good. I guess the only other thing I wanted to say, which is about this, which is on the in the book, and I didn't want to, I'm too lazy to write it down, is yeah, there's some other good examples here you might want to read. And here's the infinite stuff, but yeah, there's this sort of thing, which is like, there's stuff with minuses and with complements. That's sort of very similar to, it's like the De Morgan law kind of things where it's like, you subtract an intersection, you get a union. The complement of an intersection is a union of complements and so on. And I will say that they prove A in the book. and it's right, here's the proof, here's a proof. You know, you can sort of say, like, what does it mean to not be in an intersection? It means that there's some index so that X is not in that set, right? And so you can prove this as a sequence of if and only ifs, and part B is on the homework, which really just changes this from union to intersection. So you might, when you're doing that, you might want to look at this. I think I say that on the problem set. Did I say that on the problem set? You looked at the problem set. Okay, yeah. So I think that's all I wanted to say about index sets. Yeah, I do want to go back to induction. Do we want to take a break for a couple minutes just to break it up? We've already been here for like 40 minutes. We've got like 45 minutes left. Let's take like a 5-minute break. And I'll pause the Zoom recording. Okay, so I want to go back to induction. Where was that? Oh, sorry, it's from from last class, right? We had the those problems. And again, part of this is just the writing of the proofs, I think is what's hard. Like most of you had the ideas of the proofs, but writing it out carefully is the part that's kind of difficult and needs practice. So I wanted to try to write at least the first two down. We might talk about the third one, and then the fourth one is interesting because it's a little bit different, and that kind of is where we're going with things. But let's try to write the first two proofs down. Just how we would write it sort of formally and carefully, right? So, yeah. Okay, so induction proofs. So I think this first one is not much different from the one we wrote down, the first one we wrote down in class. Last time, but so basically the first n numbers add up to n times n plus 1 over 2, right? So that's what that says. The sum from I equals 1 to n of I is n times n plus 1 over 2. Or you could just say it as 1 plus 2 plus ... plus n minus 1 plus n equals n times n plus 1 over 2. This is more concrete to you, that's fine. There are different arguments. There is a picture proof that I think I mentioned, I don't think I talked to everyone about, but there's a picture proof that I like of this, which is, these are actually called triangular numbers. So some of the first n numbers are called triangular numbers because like think about bowling pins, 1, 2, 3, 4, they make like a triangle, you know, or like here, you can make a triangle out of them like I could represent the sum of 1 through 4 like that, right? 1 plus 2 plus 3 plus 4. And then the kind of the nifty idea here, kind of like we did with the squares, making the L shapes to make the perfect squares, right? Is I could take a copy of this and then like turn it upside down and fit it nicely in here. You see like two copies that fit together nice and snug like that? And so, again, it's nice to give somewhat more insightful proofs, but we could think of this as, right, this is 1 plus 2 plus, this is twice 1 plus 2 plus 3 plus 4. And we get a rectangle of dimensions 4 by 5. So that's 4 times 5. In other words, 1 plus 2 plus 3 plus 4 equals 4 times 5 over 2, which is kind of exactly what we're trying to prove. So that's kind of nifty. And I think that fit on the recording. Let me check. Yes, barely. Okay. Yeah. Uh-huh. Yeah, there's a little bit of an issue. Well, it's actually the same proof as this I claim, so it's a little bit unrigorous. And there's a little bit of an issue that if you have odd versus even number, like if you have an even number of numbers here, then yeah, you can like pair. You're saying like pair this up, that's n plus 1. Pair this up, that's n plus 1, and so on. But if it's an odd number of numbers and you have this kind of weird leftover thing in the middle, a kind of version of what you just said though is I can rewrite. I can, if this is S, and here I mean like sum S, not like set S. No, K, let's just call this K. If this is K, I could rearrange it this way. And then get that 2K is n plus 1 plus n plus 1 plus n plus 1 n times. But if you think about it, that's exactly what this is. This is like 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1. So yeah, I've seen the argument given this way. I like these because they're much more insightful, right? But it's still kind of like there's dot dot dots going on here. Anytime you're using dot dot dots, there's something a little bit wonky about that. I mean, maybe if you use summation notation and are really careful about what it means to reverse the sum, then maybe you could write it down without really doing induction. But usually when there's dot dot dots involved, that's when we like to use induction to make it more rigorous. Because like, is it really working still in the middle? Like if this is a million, of course it is still working, like what you just said about pairing up things, but it's not really like rigorous math to say that, So good, I think. So let's just do the induction proof. So proof by induction on n. And let's actually call this, I'll do the P of n thing. Let's call this statement. I guess I should have said for all n greater than or equal to 1, right? And then this is our P of n. So we want to show that that's true for all n. It even works for 1, doesn't it? Yeah, 1 is 1 times 2 over 2. Yeah, in fact, that'll be our base case. So base case, P of 1 says that 1 equals 1. You could check more base cases for yourself if you wanted to. And then the inductive step. So assume P of K is true. Again, a lot of books won't even write is true. If you say assume P of K, that means P of K is true, but I'll just write the words as true. And then show P of K plus 1 is true, right? Okay. Well, the left-hand side, I mean, there's different ways to do this, but you could even say what we want to show is that the sum I equals 1 to K plus 1 of I is K plus 1. I saw some people writing this nicely, which I like. You really want to replace n with K plus 1 everywhere. Right, I'm just replacing n with K plus, I'm not going to immediately get to K plus 2, I'm actually replacing n with K plus 1. And you could sort of say given, I mean, you could also say given the sum of I equals 1 to K of I is K times K plus 1 over 2. Right, that's sort of what we're assuming, what we're assuming in the inductive step. So this is the want to show thing, so it's not, we haven't established it yet. And then when I want to prove an equality, it's a little dangerous. What I saw a lot of people doing on the boards was sort of starting with this and just changing it. Whereas what you really want to do if you want to prove an equality is start from one side and get to the other. Or start from each of these and get to something common in the middle, But I think we can just start with the left-hand side here. It's not too hard. So let's start with the left-hand side of P of k plus 1, right? So the left-hand side. So start with, I'm a big fan of LHS and RHS, left-hand side, right-hand side of P of k plus 1, and try to prove the right hand, try to get that equal to the right-hand side, by a series of steps. So the sum I equals 1 to k plus 1 of I, you can think of, I could write it all out, but a nice thing about how summation notation works is that we could strip off the last term, right? We could think of this as the sum from I equals 1 to k of I plus k plus 1, because that's the last term. Is that fair? And then we can immediately use the inductive assumption, right? This is k times k plus 1 over 2 plus k plus 1 by the inductive hypothesis or something. Sometimes people say, or the inductive assumption. And from then it's just like doing algebra, right? We can we see where we want to get to. So I could pull the k plus 1 out if I wanted to. I'm not going to justify these kind of things, right? Times 2k plus 2 over 2. Is that right? And we're basically done. I mean, I'm going to actually write it exactly like that just to make sure we've gotten from one side to the other. So 1 times and then that's proving the inductive step. We sort of established the inductive step, right? And therefore, by induction, P of n is true for all n. Okay. I mean, there's really kind of a structure this fits into, right? And I really just want you to try to practice that structure first before you kind of go off on your own. Okay. Any questions about that? Oh. Thank you. Hello. Oh no. Hello. Hello. It's just low or something. Turn the gain up. Hello. 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 Sorry. Thanks. I don't know. Maybe it's hello. No, that's fine. All right. I don't know. Yeah. Thank you. I don't know why I was saying that, but let's hope it's still. Why is the camera off? Maybe something reset, actually. That's actually kind of bad that the camera went off because we read the whole proof. Yeah, maybe the whole system reset itself for some reason. But okay, well, if the camera was off, apologize, but there's the proof on the board right there. So you can pause the recording and write it all down. Okay. Okay, let's actually do the Tower of Hanoi, just how we would write it down, because I think this is an instructive, like, you're going to use a little more English. This is still mostly equations, but Tower of Hanoi. So the proposition here is for all n greater than or equal to 1, I want to say it kind of carefully. At most that many moves, right? We know we need at most a certain number of moves to solve it. There may be, we're not proving that it's a minimal number of moves, but we know like we can always solve, we know we can solve the 5-disk Tower of Hanoi in at most 31 moves, right? So for all n greater than 1, we can solve the Tower of Hanoi puzzle in at most, the pattern you guys found was 2 to the n minus 1 moves, right? Yeah, we're not saying anything about whether this is the best strategy, the most minimal. I think it is, but that's a little harder to think about how to prove something like that. So again, the proof is by induction on n. And we have a base case. We could even do n equals 1 or n equals 2. You know, we could do a couple base cases if we just want to check ourselves, like n equals 1. It's just move the 1 disk. Move the 1 disk from, sometimes they talk about being on pegs, peg 1 to peg 3, right? 1 move, which is 2 to the 1 minus 1. Right, you should check that that fits the formula. For n equals 2, I could write out like move the top disk to peg 2, move the bottom disk to peg 3, move the top disk, which is on peg 2, to peg 3, and that's 3 moves. So you could write all that out if you wanted to. So that's 3 moves. Okay, but base case, we really just need the 1. Okay, so now again, let's assume it's true. Let's do the inductive step. Let's assume it's true up to k disks. Oh, geez, you know what? I didn't even write that well. You can solve the Tower of Hanoi puzzle with n disks, is what I really should have written, right? You guys should jump on me if I'm being imprecise or something. Like, I don't want to just say the Tower of Hanoi puzzle. So the Tower of Hanoi puzzle with n disks. N disks. N at most. 2 to the n minus 1 moves. Yeah, that's more clear. Okay. So we're going to assume we can do it for k disks in 2 to the k minus 1 moves, and then try to show, and then use that to, you know, prove the k plus 1 disk case. And I guess I could have done, I didn't write the P of n thing again. I could have just circled, sorry, let me just do this again. I think in my personal life, when I'm writing induction proofs, I tend to just write like, suppose we can solve the k disk Tower of Hanoi in 2 to the k minus 1 moves, rather than just say suppose P of k is true. But especially on the board, it is nicer to have this shorthand. This is our statement, P of n, right? If I was teching, I would probably just write out in English just to have fewer symbols and stuff. Typing is fast. Okay. So right, so I really should have said P of 1 there. Like P of 1 check mark I could put there. I'm not going to switch the boards like the 5th time. And I'm not as tall as Steve, so I can't write up at the top. Word. I was telling Steve I had a friend who was a colleague here who was like 6'10", and he would often write on the back board behind this board up there, where I couldn't reach to erase or anything, just to mess with me if he taught before me in a room. Don't get any ideas. Okay. So inductive step. So assume P of k is true, namely that we can solve the k disk Tower of Hanoi at most 2 to the k minus 1 moves. So we want to show that we can solve the k plus 1 disk tower of Hanoi and at most 2 to the k plus 1 minus 1 moves, right? So consider the k plus 1 disk tower of Hanoi. We could schematically, maybe it's worth drawing a schematic of like, we could think of this as, yeah, let me just have these little pegs here. We could think of this as k disks on top. That's the little peg. So we could group this as k disks. I mean, this is again what you would write in English. Is we would group this as k disks here and 1 disk there, right? I suppose you could also do the top disk. No, could you do the top disk? I guess you could do the top disk and the k disks below it also. You could just move the 1 disk and then move the k. No, actually, that's, oh, there's a reason that's bad. Can anybody tell me? Yeah. Yeah, if I move the top disk over here first, and then I can't move this over here without putting bigger disks on smaller disks. But as long as we leave the biggest disk alone and move all of these, yeah, good. So yeah, you have to be careful with these logic with these things. So, so our algorithm is algorithm. I'm spelling algorithm. Can't write anyways. So move the top k disks. I guess this is a 3-step algorithm. From, what did you guys tell me? From peg 1 to peg 2? And this is really P of k, so this takes 2 to the k minus 1 moves. Right? 2, move the bottom disk from peg 1 to peg 3. That's 1 move. And yeah, this is the algorithm you guys told me, right? Move the top k disks from peg 2 to peg 3. Again, if I was typing tech and typing English, I might, you know, start feeling loquacious and be like, doing this, we've never moved a bigger peg on top of a smaller peg, because in P of k, we're not doing that, and we're never moving the biggest disk on top of the other k disks, you know. But that's also 2 to the k minus 1 moves. And so then you get a total, right? Which is 2 to the k minus 1 plus 1 plus 2 to the k minus 1. And then we can show that that equals what we want it to equal. All right. Okay, I want to talk about number 4. Oh, hello. Okay, so then this equals 2 to the k plus 2 to the k minus 1 plus 1 minus 1 is minus 1. So that's 2 times 2 to the k minus 1, just 2 to the k plus 1 minus 1. Right? Therefore, we've solved the k plus 1 disk tower of Hanoi puzzle in most 2 to the k plus 1 minus 1 moves. Solve the plus 1 disk tower of Hanoi puzzle in most 2 to the k plus 1 minus 1 moves. So P of k plus 1 is true. Right, and that completes the inductive step. And then by induction, therefore, you can see the structure, right? By induction, P of n is true for all n greater than or equal to 1. Okay. Yeah. Okay. So that's, just again, it's a lot of the stuff comes down to writing. I can't remember if I've said this, but I read somewhere that mathematics is the art of explanation, which I think a lot of other disciplines would take issue with. Somehow we're co-opting all of explanation, but it is something about taking abstract concepts and explaining them in a way that makes them legible to other people, and that's really what the goal of math is. Math communication, at least, is make it legible to yourself so that you can figure more stuff out. Any questions about any of that? I discussed number 3 with the, oh, sorry, Steve, yeah.
That was this awkward thing, but from the 2k to the k plus 2 to k, you get 2 times.
Well, it's like x plus x is 2x.
Oh, okay.
Yeah. Yeah, somehow that looks weirder when you read it with 2 to the k's, but yeah. Okay, so number 3, I found in a book or in someone else's handout or something. And I will say you could do it by induction, but I think I talked to some of the groups, and really it's almost easier just to say, like, if the price is even, I can just use, if the price is 2M, I can use M $2 bills. And if the price is 2M plus 1, well, that's at least 5. 2M plus 1 is at least 5. So I can use a $5 bill to get down to an even price. So you could write out, like, explicitly how many of each you need, and you could just do it. I mean, that's where you could really, if you give a number, you can explain exactly in terms of that number how many of each bill you would need. And so I don't really think, it's kind of interesting to try to think about as an induction proof of how you would go from one price to $1 more. I think we talked some about swapping out 2 2s for a 5 or a 5 for 3 2s. And being able to argue that you could always do that. And so, like, you can give an induction proof that way, but I don't have time to really go through it, because I do want to get to this idea every integer greater than 1 has a prime divisor. So I claim this is something we can prove by induction, but it's weird, right? Because if I want to prove, like, 743 has a prime divisor, it's probably going to not have anything to do with 742. So we're not going from one step to the next, right? So proposition: every integer greater than 1 has a prime divisor. And for this, we need something called strong induction. I mentioned weak induction, right? We've been using what's called weak induction. People just call it induction, but we need strong induction. So let me just say what that is. That's basically saying, let's use the ladder metaphor, right? The ladder metaphor is like, we can get on the ladder, we can get from one rung to the next. But I guess you could also say we can get on the ladder, and then wherever we are, we can get to every rung below that, right? Like you're not really saying anymore by saying wherever I am now, I can get to every rung below that. And maybe I can use that whole logic to show that I can move to the next rung. Like maybe I can actually like jump 5 rungs at a time or something. You know, so you actually want to use something earlier than just the previous one. So strong induction says, if we want to show P of n is true for all n greater than or equal to n naught, right? That's kind of how we said it last time. Then we show 2 things. One is the base case again, that P of n naught is true. And then 2 is for a fixed k, if P of I is true for all I sort of from n naught up to k, right? So we're going to try to use all of the previous steps instead of just the one previous step. You see what I'm saying? Like we're saying if P of I is true for all of those, then P of k plus 1 is true. So that's sort of using, like, it's using all the previous steps, not just the one previous step. The previous steps. Because, okay, and then like that's what's called strong induction. If you show those 2 things, then P of n is true for all n greater than n naught. It's a little bit abstract and weird looking, but it's helpful in a situation like this. Let me just sketch. If we're going to run out of time, let me just sketch the idea here. Which is, so the base case could be n naught equals 2, right? So if we want to prove this, let me just say proof sketch because I'm not going to have time to write this nicely. N naught equals 2. 2 has a prime divisor, namely 2. Right? And then the inductive step is going to be something like the following. Suppose we know all if you just think about what this strong induction says, it's what we're really saying is we know all integers 2 less than or equal to I less than or equal to k, every integer I between 2 and k has a prime divisor. Right? So we're not just using k, we're using everything from between 2 and k. Right? That's kind of the inductive assumption that's down here. And consider k plus 1. Again, just because we're going to run out of time. If k plus 1 is prime, we're done. Right? Otherwise, k plus 1 is composite. I guess that clock's a little faster. We have 3 minutes for printing this. Otherwise, k plus 1 is composite. And if k plus 1 is composite, that means it has a divisor smaller than k plus 1, but at least 2. So if k plus 1 is prime, then it has a prime divisor, done. If k plus 1 is composite, then I could say like there exists an I in this range such that I divides k plus 1, right? But let's just say it in words. K plus 1 has a divisor, sort of a non-trivial divisor, I satisfying that, right? It's not, primes can factor into 1 in itself. So this is saying it's not factoring into 1 in itself, right? It's factoring into, it has a divisor. But then I has a prime divisor by the assumption. And thus so does k plus 1. Because sort of like if A divides B and B divides C, then A divides C, right? Like I's divisor of k plus 1, I has a prime divisor. So that, yeah. Does that make sense? Sorry, I'm rushing this a little bit at the end of class, but like, I'm just trying to give you the idea. We'll talk a little bit about strong induction and the well ordering principle in the next class, but that's kind of the idea. It's like, this still is an induction proof. It's like, yeah, we know everything up to our number that we're under consideration has a prime divisor. So either it's prime itself, which has a prime divisor, or it factors into something smaller, and it has a divisor that's smaller. It factors into things that are smaller, and those things have prime divisors. So it lifts back up to k plus 1. Yeah. Okay, great. Like I said, sorry no office hours this afternoon, but I will be around Friday. The recording came out okay, so yeah.